the first one, the theory explanation. The second one, a concrete example to see the whole procedure. Yeah. All right. Problem 24. This Huffman code is used in signal compression. Signal compression or data compression. Yeah. Because the data can be treated as signal. Yeah. What's the signal? The digital signal. Not analog signal, digital signal. Yeah. You know, a set of numbers, digital signal. Okay. Yeah. So given a sequence of characters and their frequencies, characters, yeah. We know we use characters to represent data information, right? Data represented in characters. Yeah. But the occurrence of each character, the percentage of for the occurrences different. We call that frequencies. Yeah. Yeah. So frequency, percent of the occurrences of for each character. Yeah. All right. Find a way to assign a binary code. Because when we encode data, we can only use the binary format, 0101, binary format. So then we can send the binary format to the other side of the communication channel. Yeah. So then the other side can decode the information. Yeah. So binary code each other, each character, so that the encoding scheme based on this code on the sequence of the characters is optimal. What do you mean optimal? The number of bits is the smallest. That's optimal. Because we want to use as small number of bits as possible. The more bits you send, you know, it takes longer. You have more data to send. Yeah. For the same amount of information, we want to use the minimum number of bits to send. That is the goal. How to do it? That is the problem. Yeah, so this problem. Yeah. So that person, Huffman, solved it. So people call it Huffman code. Yeah. All right, the Huffman coding. Yeah. The procedure. Very interesting. Yeah. All right. Here, there are two steps, encoding step and a decoding step. So when you do the translation, so you have to, preserve the original information. Yeah. Convert the character sequence into a bit sequence. That's the encoding step. Okay? Yeah. But you want to get an optimal solution for the encoding step. Then, decoding step. Yeah. Recover the character sequence from the encoded bit sequence without any error, our goal. Yeah. So you have to do that reverse procedure, recover step. Yeah. All right. Actually, the decoding step, very easy, straightforward. The hard part is the encoding. How do we define that encoding scheme? That is hard. If we solve that problem, the remaining, straightforward. Yeah. All right. Yeah. There are many ways to do encoding, decoding. Yeah. Yeah, definitely. If you, try, yeah, everyone has an idea, you can try, but we want to find the most efficient way. Yeah. The shortest bit sequence, that is our goal, the criteria. We use optimization criteria. Yeah. let me use a simple example to explain the idea. Yeah. Here, suppose we have the data like this. We use 6 characters, A, B, C, D, E, F. For each character, the frequency, the number of thousands, okay? 45,000 occurs. So, we do statistics, in a large amount of text. B appears 13,000, C 12,000, D 16,000, E 9,000, F 5,000. Okay, total. Yeah. So here, when we use the our coding method, here we compare 2 different ways: fixed length code word and a variable length code word. Fixed length, each one we use 3 bits. 3 bits. That's so easy, right? But if you use fixed length code word, look at how many total bits do you need. Yeah. We compare. We can also use the variable length code word like this. Different number of bits. Now we want to compare which way can give us fewer number of bits, total bits. Yeah. We consider 100,000 characters. 100,000. Okay? Yeah. These numbers adding together, 100. The unit 1,000, so 100,000. Okay? All right. The first one, you can see easily, 300,000. 300,000, because each character 3-bit. You have 100,000 characters multiplied by 300,000 bits. Okay? Yeah, the first one. Second one, let's do calculation. For A, each A, we only use 1 bit. For 45,000 A, we use 45,000 bits. All right. B, each B, we use 3 bits. For 13,000 B, we use 39. 3 times 13,000. 39,000 bits. C, 3 times 12 bits. D, 3 times 16 bits. E, 4 times 9 bits. F, 4 times 5,000 bits. Let us add up all these numbers. 224, the unit is 1,000. So 224,000 bits. You can see significantly smaller than that fixed length scheme, right? Approximately 25% improvement. That's significant. Yeah, we like that. Okay, so here you get the idea. So when we carefully choose the number of bits for the code words, then we can make the total bits as small as possible. All right, the question. How to get the variable length code word assignments? That's the key question. How do you get that? How do you get that to make sure you get the best solution? Right? Yeah. Okay. Greedy algorithm. Here. So, yeah. The greedy strategy, yeah, we can try that. But the issue is, how do you apply the greedy algorithm? There are many different ways to use the greedy algorithm, right? Yeah. Here it is not that obvious. Yeah. Here you have to use it in a very smart way. Yeah. Not that simple. Yeah. Yeah. But we have some basic principle. The principle is we use fewer bits for symbols with higher frequency. So look at here. The frequency is high, 45,000, and we use fewer bits. Okay? The frequency a little smaller, so then we can use more bits. Okay? The frequency very small, then we use more bits. Yeah. So that's the general principle. Yeah. To get precise way to do it, yeah, we need much better way to do it. Yeah. That's not easy. Yeah. All right. Next, let's look at encoding, decoding. Yeah. We want to look at, any property we need to pay attention to when we do encoding, decoding. Yeah. All right. Here, let me ask another question. Why not using 1011 here? Okay, 10 here, 11 here. Then we can make fewer number of bits, right? Yeah. That question we need to answer. Yeah. Otherwise, we may do it in a wrong way, right? Yeah. So we need to answer that question. 1011 here. All right. Let me see. Yeah. Think about if you use 11 for, then you will get trouble. Because when you use 11, okay, when we see 1110, okay, all right, because when we get a sequence of bits, when you see this, all right, excuse me, when you see 11, do you know you get a C, or when you wait one more, 111, you get a D? Because 11 could be this one, and it could be 111 for this one. So you will get confused. That means your coding method is bad. Your coding method cannot avoid confusion. Okay? So when you design your coding method, you have to avoid any confusion like this. Okay? So we do not want this to happen. So we set a rule for it. So we call it prefix codes. When we design code, we need our code satisfy this prefix condition. Yeah. So that is the rule we need to follow. Okay? What's that? No code word can be a prefix of some other code word. Yeah. So no code word, prefix of another code word. You need to detect, you need to check this rule. If this rule is violated, you should not use that code. Okay? Yeah. So when you design, you need to use this rule. Okay? Yeah. All right. All right. So encoding by concatenation. Yeah, because when you have many characters, each character you assign a code word. Then when you put all the characters together, then you do concatenation, right? So you get long bits because you cannot use any separators, right? Yeah. So that's the number one. Example, here we can use a simple example. ABC, for example, in our question here. Suppose we want to encode ABC. You just pack all these bits together. So 0, 1, 0, 1, 1, 0, 0. Okay? Yeah. So that's the simple way. You can do the encoding. Decoding through code word character translation. Also straightforward. Yeah. So let's look at decoding. Suppose we have these bits. How do we do the decoding? Okay. When you see 0, because 0 matches character A, you just do the translation A. Then you check 1, nothing match 1, 1, 0, nothing matches 1, 0, 1, 0, 1, yeah, you'll find the character B. Okay? Then 1, 0, 0, you'll find character C. Okay? So you do the translation like that. Yeah. The translation must be unique. Okay? Yeah. So when you have that, then you have no problem. So your code word design should be all right. All right. Okay. Yeah. So that's the theoretical part. Yeah. Next part, I will use one example to explain how to design this Huffman code. All right. Yeah.